Hello and welcome back. Now we know how we can tune our own models to create the best kind of model. But what we have seen is that it takes a lot of time. And this is not always feasible, especially if there are already pre-trained models out there which we can use. And this is exactly what we do now. Because you'll see that here I'm training this model on my own computer and I don't have a GPU, and it still will work. Because all we do is we use a model which is already out there, provided by an institution like for instance Google or Amazon or any other kind of big company which used a lot of resourcing power to train those models, and we can use those models and adjust it to our specific use case. So if there's already a pre-trained model out there, it makes sense to use it. In case there's not, then of course it's always good practice to create our own model and then use tools like Keras Tuner, for instance, to get the best kind of model we have. So here I'm gonna start here with importing the libraries we need. So in case you have not installed them on your local machine, or you can also of course continue in Colab if you want and then download the model weights afterwards. But here I will do it locally, as I said, and I need to install something. So I need EfficientNet because we will leverage the EfficientNet, which is one of the pre-trained models. Of course, you can also use other ones, but here we start with the EfficientNet. And we also need, of course, the TensorFlow datasets because we want to rely on the same dataset, so the rock, paper, scissors dataset, which we've used before. Okay. So at first, I will import something. So in case you have not installed it, you need to run pip install, and then you say TensorFlow datasets, just to get the rock, paper, scissors dataset, and also pip install like that, and then you say you want to install basically EfficientNet, EfficientNet like that. Okay, in case you have not pre-installed the EfficientNet, then you could run this command just to install it, or also do it via pip using browsing to your Anaconda folder. That should also work. Okay, so that would be the options which are available. I just commented out because I've already installed it, and then I go to new line and import what I need. So, of course, all the libraries we import now, if you don't have pre-installed them, if you want to follow along on your local machine, you have to install them first, like the pip install command, okay? So, I will import TensorFlow, as TF, so it's just an abbreviation, and then I will continue, so from TensorFlow, Keras.models, I want to import model, for now. Okay, import a model. Then I will also import a few things. In addition, sometimes we don't use all of them, but it's most of the time I'm importing the same libraries, so that's why I'm importing them. So TensorFlow, of course, it's always best practice to only import what you need, right? So Keras.models, or so layers, because we want to import, in this case, import global average pooling, and 2D. So because we are dealing with images, so two-dimensional arrays in this case, or three-dimensional arrays with color channels, and then we say dropouts. I also want to import the dense layer, and let's also import the flatten layer. Okay, so these are the layers we're going to use, and then we want to import EfficientNet, like that. Import EfficientNet, and also .tfkeras, and then say as EfficientNet. So EFN is just an abbreviation I'm going to use here now. And then I also want to import NumPy as NP, and I also want to import the TensorFlow underscore datasets here as TFDS. Okay, so TFDS for short abbreviation again. Okay, so that's one we want to import here, and then we want to initiate. Let me actually run this, and let's see. I got import. Where is it? Import. Of course, I need to spell it correctly, like that. One more time. Import. Just a second. Import like that. Okay. So that's fine. Okay. Just a warning here. Doesn't matter for now. So what I want to do now is I want to actually my F. Simply call it EFF for EfficientNet, and I want to EFN dot EfficientNet. And here I want to call the B0, I'm going to use this one here, and I say that the weights, and that's exactly the point. Here we have pre-trained weights we can use, and we refer to the ImageNet weights, which are available here, and then I say include underscore top is equal to false. What does this mean? Well, basically we want to have the EfficientNet, but we want to cut off the last layers. We don't want to have the final layers because we want to, of course, append our own layers because we only have 3 classes at the end, right? And the EfficientNet might not have, or the pre-trained model you use might not have 3 classes. Sometimes one of them, for instance, has 1,000 different classes. But if you want to do a classification on 3 classes, and of course we want to train the last layers in the model, right? We want to retrain them because we don't want to classify, for instance, planes or cars or anything, but we want to classify, in this case, rock, paper, or scissors, right? So that's why we do not include the last layers in this model. And we also define input shape, so input underscore shape in this case is equal to, and then say it's 32 by 32 times 3. So this is simply the size of the image. We say 32 by 32, and we say it's in this case 3 color channels. Remember, we dealt with 1 color channel when we did the training on the Colab, right, before, but this time we're gonna go with 3 color channels because the original efficient net was trained off on these kind of pixel sizes for images and on 3 color channels. Okay, so that's that, and of course we can run this. So let's see, let's run that, and you see it now, we're done. Okay, so far so good. And then of course we need to then continue and say, for instance, as I said before, we don't want to include the top layers, and we want to make this, we want to keep those weights we loaded here, right? We loaded the image weights, ImageNet weights for all the layers in the efficient net without the top layers, and now we simply say f.trainable, trainable is equal to false, right? That simply means that all the layers in the network up to this point will not be trained when we run the when we do our training, our own training. And then we also specify, okay, what should the network look like? We say x, or you could name this whatever you like, is simply f.output. Output. That simply means we want to get now the last layer of the current efficient net, and this will be stored in x. And then we add a few additional layers. So we say x is equal to flatten, like that. And we instantiate it and say here x, here. And by the way, here, as you can see here, we do not use the sequential API here. You probably could also use it, but here we're going to go with the functional API, which is the second API which is available in Keras. So we simply say we get the output here and store it in x. Then we use a flatten layer, put the x, so basically this one here, inside this flatten layer. So the flatten layer is on top of x. It's not inside, it's basically on top of x, right? And it's stored again in the variable x. Of course, again, you can rename it, but then you have to rename it in the next step as well. So now we say x is equal to a dense layer here, and we say we have 1024 neurons in this layer, and we say that the activation is equal to reload, okay, like that. And of course we need to stack it on top of the x, so the previous layer which we defined. Okay, so we got this as well, and then we add also a dropout layer just to avoid overfitting. So say dropout 0.5 and put an x in here like that, and then we simply define the output layer. Of course, you can also, out is equal to, and now we simply say this out is simply a dense layer. And now how many neurons do we need? Well, let's think about, we have 3 different kind of classes. So we have rock, paper, and scissor. So again, we go with 3 output layers here, or basically output neurons here, and say activation is equal to, in this case, softmax, right? Because we got a multi-classification problem, so we go with softmax, not the sigmoid. And of course we need to put this on top of the x, right? And this x, again, here, this one here is referring to this layer here, right? And this one here is referring to this layer here, and so on, right? So that's how that is stacked. Okay, and then we can simply say, now here, say model is equal to model, and now we simply need to put in the input layer as well as the output layer. And the input layer is simply from our efficient net, so simply dot input, which is simply the first layer from this whole fnet, right? And the output layer, of course, is we're referring to out here, right? Because we stack basically those layers on top of the efficient net layer. So the input is efficient net input, but the output is now this out, which we defined up there, right? This one. Okay, so we got this as well. And then finally, of course, we need to set here, let's go on here, the compiling the model. So model.compile, compile like that. And we simply say, put in the this here away, model.compile, and you simply specify, okay, the optimizer is equal to Atom in this case. Of course, you can use other ones, try different ones if you want. And then the loss is equal to, again, it's tf.keras.losses like that. And we specify .sparse, categorical cross entropy, here we go. And then we instantiate it. Of course, you can put in additional parameters if you want, and attributes, but in this case, simply say, leave it empty and say matrix finally is equal to, and we can do it accuracy because it's a classification problem. Okay, accuracy like that. So we got this as well. Okay, and let's actually run this, and it's run. Okay, and then of course the next thing is that we then will load the data set and of course we want to prepare the dataset, because here we are dealing with locally environment. That's why of course I need to again load the rock paper scissor dataset. But this is something we cover in the next video. Until then, best guys.